Today, I'm pretty excited about today. We're going to be hearing from Greg Snow, who's here, who's going to talk about object-oriented programming, or specifically the our class this time. So, thank you so much. We'll get started.
Thanks. So, I'm Greg Snow. This is actually, I like this, putting together this presentation. This was one of the ones I volunteered to do this because I knew about R6, but I also knew that I needed to learn more about it. So, sometimes I present this just like, okay, here's stuff I know, dump it, talk about it. But this one was one where I learned a lot putting it together. So, hopefully other people will enjoy it and learn as well. Something happened in putting my presentation that some of my bells and whistles disappeared and actually the date disappeared. So in September, I'll try to find a new one to post to the GitHub page. But one of the things I added was a quote in there that there's a lot of programming that says every program contains at least one bug and can be reduced by at least one line. Therefore, by induction, every program can be reduced to one line that doesn't work. But I put that up there just as a thing is I think that the best way to learn this really is through a bunch of examples. Because I have a lot of example codes. Hopefully, everything is in there and working well. But the examples were meant to be examples, and what I was learning and help learn in that. And there's a lot of things like, well, you could have added this, you could have done this differently in that. Well, yeah, and I could have reduced all of them to one line that didn't work as well. So, take them as examples, and some things I would have done differently if I were doing this for actual production code. But one of the first things is, well, what is object-oriented programming? And so one thing to think about with that is, well, as opposed to what? And so kind of the two fields that get contrasted is functional programming versus object-oriented programming. Now, there's lots of others, but those two seem to be the ones that get contrasted here. So functional programming is basically you have a function whose results are based only on the inputs. So whatever is input determines what comes out. So the function should not depend on anything else but its inputs. So because of that, the same inputs, you should get the same outputs. So if I ask for the square root of 4, I should get 2. And it's not going to look at anything else. There's no options, no other status. Square root of 4 should always give me 2. And so the square root is an example of a functional thing there. Okay? Functions also only return their results. So a square root function would return 2, and then me as the programmer, I decide what to do with it. It will never stick that into a variable for me. I have to assign it. Okay? Because of that, inputs might be copied internally. If it's going to modify something internally, it will copy everything so that it doesn't change the original data. So, if I ask for the square root of x, the function square root should not change x at all. Okay, x should stay 4 or whatever it is. If I want it to be replaced by 2, then I as the programmer need to say, replace x with 2, what's your true, or with the result, what's your true. Okay? Functional programming is clean, simple, and predictable, but sometimes redundant, inefficient, and a pain to pass everything around. Because in functional programming, since functions depend on their inputs, you have to input everything. Okay? They can't look at options, they can't look at other things. It has to be based on just the inputs, so you have to keep all the inputs and pass everything around. One thing that people got frustrated with functional programming is said, well, I like the functional approach, but let's change things a little bit. And so they came up with this idea of pass by reference, which is a great, brilliant, and horrible idea. Okay? It makes things easy, including shooting yourself in the foot. So it's easy to mess up as well. But the idea is that instead of passing the data to a function, I will pass a pointer to where the data is. So I'll just tell the function where in memory the data is stored, and then it can go and look at the data. And so this means that it's not going to have to copy that data, but that also means there's nothing that stops that function from changing my data as well. And so that's where you can get into real problems with that. So it's nice that a function can access data without having to copy it, but it can also change the data in place. Sometimes we want that, but sometimes it has unintended consequences. I've actually seen some code in, I think it was C++, where people weren't sure if a function changed their data or not. So the whole purpose of this was so I didn't have to copy my data. but people to protect their data would make a copy of it and then pass the copy to the function. So it ended up, while it was supposed to save copies, it ended up causing more copies sometimes. Okay, so it becomes less redundant, more efficient, less of a pain in some ways, but it's not clean, not simple, and not predictable in what it's doing. So that's my reference. Seems like a great idea, and for some things it's really useful, but it also causes a lot of problems. Okay. So object-oriented programming was kind of the next kind of evolution of, well, we need to get something a lot cleaner than passing by reference. And so now it kind of turns, instead of looking at a function, starting with the function and saying, okay, how do I pass the data to the function? Object-oriented programming actually kind of starts with a data object, and then you figure out what methods, which is the fancy name for functions, are going to work on that data object. Okay? The object can be modified by its methods, so there is a way to change the data programmatically that you don't always have to assign it like in the functional, but you can restrict who can change it. The object can change itself, but you can restrict it that outside of the object you can't change it. So you can have things within your object that can only be changed the right way. So you can control how it's changed. So it's just not arbitrary and you can change anything like references did, but you can still have things changing without having to make all these extra comments. Now, functional versus object-oriented is, well, R is kind of this unfolding mixture of both, plus other programming things in that. Here's a quote by Patrick Burris, who's a thing. He says, as long as R stayed in Ross and Robert's computer lab, R can be perfectly clean and beautiful. The moral of the story is that if you want to create a beautiful language, for God's sake, don't make it useful. Okay? So sometimes people say, well, why isn't R just purely object-oriented? Or why isn't it purely functional? And it's like, well, because it wanted to be useful. And if it's useful, it has to be a mix of things. So because of that, we get kind of these strange combinations of things have to evolve over time. But why should we use objects? First, some of the things to use objects. Well, when you're using an object, you can have multiple variables that you're keeping all together inside one object. Okay? When I started first using the S language pre-R, I remember I would go in and I would create a variable named X and a variable named Y, and then I'd create, okay, and there's another variable X, but I didn't want to delete the other one, so I would have X2 and Y2, and then I'd have XX and YY, and then I'd have X, X2, and X3 that correspond to Y2, and then I had X4 and Y3, and it was just confusing. So data frames were great, because you could at least have X and Y, and then a different X and Y, and all that. Well, a data frame is one type of an object. Okay? So objects are nice, and you can kind of have all these different pieces together, and then when we get to the R6 objects, they're kind of nice in that you have all the data plus methods specific for that type of object all grouped together in one place. Okay? With objects, you can keep information between function calls. So if I call a function and it computes some information that's not part of what I want the function to return, but is something that might be useful, I need a way to store that. And an example of that kind of in the base R is like the LM function. The LM function calculates a lot of things to get to the regression, and it says, well, you might want this in the future. If you don't want to have to recompute this when you're doing some of your diagnostics or that. So LM returns this great big huge object that has all of these extra pieces to it, and just prints out part of it. But with the LM, that's kind of the simple LM is what we call an S3 object. Because it has all this extra information, just tells you what you want, but if you do diagnostics based on that, it says, oh, I already computed these matrices for you. You don't have to recompute it, you can just reuse these ones. So it's nice to carry that extra information around. Okay? With objects, you can keep track of that information. You don't have to recompute things, and you can do that by avoiding global variables and options. And then the last one is, why use objects for all the cool things you're doing. Isn't that the reason we do everything that somebody else says is cool? Okay, so I want to talk a little bit. Is one of the great things about object-oriented is it's a way to do things that you can also do with global variables, but object-oriented is cleaner than global variables. And so here's a quick quiz that I like to introduce as to why global variables aren't good. So if I run these two lines of code, x gets the value of 10, y gets the value of this function that uses global variables of x. So after I run those 2 lines of code, what is the value of x? The answer is we have no idea. Okay. The only way to know, well, I mean, we could look at x, but because we ran a function that uses global variables, it could have changed the value of x. So we'd have to examine the code in x in the function, or we'd have to trust that it doesn't change x even though it changes other things. But the thing is that the reason we don't like global variables is after running code like this, I don't know what x is anymore. Okay. It might still be 10, but it could be anything. So I'm not the only one who doesn't like global variables. So Bill Venerables, these are all from the Fortunes package. So he says, I wish, I don't know what it's called, but less and minus operator is one way to do global variables. Says, I wish it had never been invented as it makes an esoteric and dangerous feature of the language seem normal and reasonable. If you want to dumb down R or S into a macro language, this is an operator for you. Bill Venerables is one of the R4 big famous persons. You wrote one of the first books, Stephen Breitler, who wrote kind of the S and R Bible books. Hear that. Another Fortune, somebody slightly less famous than Bill Venerables. The only people who should use the assign function are those who fully understand why you should never use the assign function. I was actually, that was originally, I read that about it, different functions, Perl, and I plugged in assign in here, use it for R. Somebody thought it made a good Fortune. Or here's another one. So Thomas Lundgren, another way people try to deal with global variables and something is Thomas says that the answer is sparse. You should really usually repeat the question. And somebody asked a question about that, and I was trying to explain why that was correct and you should never do this, but I want to say, well, I don't know everything. Maybe there is some reason. And so I said, how can I say, don't do it, you fool, but without offending anybody? And so first, it ended up coming out as personally, I've never regretted trying to address my own future stupidity. So I think that was my first quote to make it into the Fortune package. So one of my claims to fame is that I made it into the Fortune package. Okay. So just a quick history of object-oriented in R. So the original so everybody know S was the language, but R is the dialect of. So there was the S language in the 1970s. It evolved over years, and R kind of ran on top of that, and then the main classes kind of disappeared. Basically, the third version of the S language added object orientation as a very simple case. And this is what functions like LM use. And so basically, you can have a data object that has a class, and then you can have a generic function. So something like summary. If you call summary, if I ask for the summary of X, then the summary function looks and says, well, what is X? And it looks for a class information. If X is just a numeric vector, then it does one type of summary. If it's a factor, it does a different type of summary. If X is the result of a call to LM, it does a very different summary. And so that data, so all I need to remember is the summary function, and what type, it depends on what type of object it does the right thing. Okay? And so it's quick and simple, but there wasn't really any checking in this. I've seen lots of code where people would call a method on a different type of object. And it was kind of a trick that worked for some cases, but there was no checking, and that you could say, okay, I want to call the summary function for LM results on a simple vector. And then you would just get strange errors because it was expecting there to be certain fields in that object that weren't there. And so some people complained and said, well, this is nice and this is a start in the right direction, but we're, without this checking, it's easy to mess things up as well. Okay? So when S4 came out, they added a more structured version of object-oriented, which is called S4 because that's what it was. So I don't know we don't have an S1 and S2 because I don't think they have true object-oriented stuff in those. We just refer to them as S3 and S4. So in S4, they kind of made it more structured. So now you had to register an object. You had to say, this is my type of object. It will have these slots in it, so this type of data, and then we will register that these methods have to work with it. And so it made it safer because only the methods would only work on the right type of object and would guarantee the right thing. You had to think a little bit more up front which some people think is bad and some people think is good, and some of us think, well, it's both, and we don't want to do it, but we recognize it's a lot less flexible. And this was met with very mixed results. And sometimes people, a lot of people coming from computer science who like the more structure were saying this is the greatest thing ever. And people who were used to the old way and didn't want to have to think up front were saying this is the most horrible thing ever. And if you look through the our health and S News mailing list from this time, you get, wide ranges of opinions on how they work. R developed what they call reference classes. So this was a way that looked more like what is really considered the object-oriented languages, Smalltalk, Java, C++, others like that, where it's really, the methods are now not generic functions, but they're actually functions that are attached to the object more directly. The reference classes were based on the S4 method, and they still ended up being somewhat complicated. Okay? Because this was the next step after S4, but it was only in R, some people started calling these R5 objects. But the authors that wrote them didn't like that. They're saying we weren't trying to just do the next step in that chain. So they were complaining when people called it, but it was easier to say R5 than reference classes. So then we get the R6 package, which basically says, well, we'll kind of skip R5 as a name, but R6 makes sense. But basically it goes back and it says, well, let's do S3-based objects, but like the reference classes, and let's simplify everything to be nice and work well that way. And I actually read something where Hadley Wickham, he had originally used reference classes for his ggplot2 package, and when R6 came out, he liked it better. He switched things over to R6, and he said that it set up ggplot2 like 5 times. So they're faster as well as. So this is what if you're going to get into object-oriented programming, this is why I like R6. It's the most mature of these, really captures what people are trying to do, and I think it's the simple for object-oriented programming and straightforward. Okay. So what are R6 objects, and how do we create them? Okay. So it's the R6 class is the function that creates an R6 object. Okay. So basically, you pass it a set of lists that are going to contain all the information that you need. So variables are called fields and functions are called methods, but you just kind of pass them in there. Once you've created that, then there's a method called new that creates a new instance of that object. And then within the coding, you reference the different slots using self $sign and then a variable for method name or private $sign variable name. And we'll see more examples. I think it's easiest to see from examples, so we'll get to those there. But there are 3 possible lists that you can send it. So public is these are the things that a user of this object can access. So variables that they can look at and change, methods that they can call from outside of the object. So when you're using the object, you have full access to the public pieces. There's another option you can do that are private pieces. So this is if you want something protected, is other methods within that object can access the data in a private space, but outside, when you're just programming regularly, you can't change those. You can't access those unless they're successor functions. So that gives you that control more than the pass by reference idea, is that you can say, I only want certain functions to change the value of this variable. You make a private, and then you have to set those things up that way. And then there's last one, active. I'll get to some examples of that as well. That are a list of active bindings. These are basically their functions that act like variables. Okay. And one of the things that I think I've got some examples of that. I'm going to show that. So there are 4 basically special methods that every time you create an object, these will automatically be there, but you can override them if you want to do something special. So initialize will automatically be run every time a new object is created. So if you need to set something up, you set that up in the initialize function. Finalize is run when an object is, well, technically when it's selected, but when you delete it, it'll run finalize So if you need something cleaned up, so if you opened a connection and you want to make sure to close it, or you create a temporary file and you want to delete it, you put that in finalize, and that will be run once you're done with everything. Okay? Clone makes a copy of the object, and it has a default method that just makes a simple clone. But if you want to do something special every time you copy an object, you could extend that method as well. And then print will give you a basic display of what's in the object. But if you wanted to say, okay, when somebody prints this, I want it to look nice or only show this information or whatever, so you can overwrite any of those to do extra stuff. Okay. So first is just an example. One of my other claims to fame is that I wrote one of the functions that created progress bars in R, put it into a package, and then Brian Ripley called it, I should have kept the email, but I think his phrase was one of the ugliest I've ever seen. And so then he wrote the progress bar code that is in R. So I didn't write what's progress bars, but I inspired Brian Ripley to do it by writing something that was useful enough and ugly enough that he had to write something better. Okay? So there's actually three sets of functions in R that are there because I wrote code that Brian Ripley would have to write better code. So the progress bars are one of those. Okay. Here's something I might do using the built-in progress bars. And my computer on Windows, I use the Win progress bar. But if you're not on Windows, there's a text and an PK version of the bar. Okay. What I'm doing here is saying, okay, if I want to replicate Gossett's lifetime work, so the student key distribution, I have a simple simulation function here, generates n values from a normal distribution, then calculates the mean divided by the standard deviation over the square root of n, and then if I run that a bunch of times, look at the quantiles, that essentially will give you the that row on the table, student's key distribution. Okay? So now I want to run it here 10,000 times using the replicate function, but I want a progress bar so I know how far through it is. Okay? So the standard way is I would call the win progress bar function, save the results into a variable that I call here PD for progress bar. Down here, inside of my function I'm running, I need to get the current value, add 1, and then use set win progress bar and give it the new value. Just increment the progress bar by 1. Then I run my student sim function, replicate, runs that 10,000 times for me. This will pop up the progress bar. I'll see it, go across to 1,000. And then to close here, gets rid of it at the end. Okay. So that was Brian Ripley's way of doing it. I didn't like his interface as much. When I told him that, he said, well, you're welcome to write a wrapper function around it to make it look like you want to. And I was like, well, I know that, but he's Brian Ripley and I'm not, so his stayed. But I wanted my version, and R6 actually makes what I think is a nicer version of it better. It makes a great example for this. Okay. So first, this is longer to get started, but once we actually use it, I think it's more clean. So here's my progress bar, and I'm actually going to scroll down a little bit here, and I will put this code, or I'll get this code to somebody who can put it onto GitHub for us. I'm going to start here with the private list. So, and I could have made these public, but I wanted to show private versus public here. So I have two things in the private list here. So one is the progress bar, and it's just a placeholder. The other is I will be my incrementing variable, and it starts off at 0. And apparently one of the things that I lost is I had before my finalize function should always be private. It doesn't enforce it yet, but they said in the future they might enforce it. Is the user should never call finalize. It should only be called when it's deleted. So it should be in the private here. But all my finalize is it calls the close function on my progress. Okay. Scroll it back up to the top. So public is a list. So I have a couple different functions in here. So the first one is initialize. So I wanted to do something special when I start up. And when I initialize, I need to call the win progress bar function to create the progress bar. So I'm still going to use that one for all the functionality, and I'm just doing my nicer wrapper around it. So when it initializes, it's going to create the progress bar. My function is going to have a max, what's the maximum value for the progress bar that was passed through. Here's my finalize. I haven't moved it, there should be in the private, but it just closes that. But referring to as private $PV says that's the one within the private space of this object. Okay. My increment function just says add, so amount is going to default to 1. So if I don't pass any arguments to it, it's going to increment I by 1 value, and then it's going to call set min progress bar, which will actually visually make the change. And do that, and then also do a reset, so I can reset it back to 0. Because I might run my loop and then say, oh, whoops, I want to do this instead, or rerun the loop. Rather than closing the progress bar and reopening it, I can call reset and just reset it back to 0, and then I use it there again. So we use this. So when we run this, so I'm going to say, this I'm going to PV the prog bar $. So prog bar was the return from the R6 class function. And so it's the one that I'm going to use to create any new progress bars I do. So I say it's going to go up to 10,000. I put this reset in here since it defaults to 0. I don't need this the first time through, but I usually put it in my code anyways, so that if I run this, oops, I needed to change something in here, it's there in place. When I run this again, it starts at 0 and then moves from there. But before, in the functional form, I had to get the current value, add 1, and then set the value again. Now I just put my progress bar $P, and it increments it by 1. So each time through the internal loop the replicate does, it's going to increment my progress bar, and it's going to look, the same as when I ran it the other way. But I just think this looks a little bit nicer and a little bit cleaner than having get progress bar PV, add 1, set progress bar. So I like this a little bit better that way. When I run my function again, it does everything here. Again, now if I remove the progress bar, that's going to call close. I just put the garbage collection function in there because it doesn't actually you don't see the progress bar disappear until the garbage collection runs. So this explicitly runs garbage collection. The garbage collection is just inside of R. When you stop using a variable, it's still there in memory somewhere. It's just nothing's pointing at it. And occasionally R runs what's called the garbage collector, and it goes and checks for all these variables that this memory isn't being used anymore, and so it really should be recycling now because it means it's available again. But that's what runs and closes everything. So. Okay, a little bit nicer here, or if I want to go on beyond this, it's kind of nice. So now I want 2 loops. So I want, I ran before replicate for 1 sample size. Now I want to do it for a list of, or a vector of different sample sizes here. So I can create an outer progress bar. So pd.o is my outer progress bar. pd.I is my inner progress bar for my outer versus inner loop. And so I'm going to do lapply across my sample sizes. Inside of that, I'm going to increment my outer progress bar. I'm going to reset the inner one, and then I'm going to call replicate, and inside the replicate function will increment the inner one. Okay, so if I run this code, it's going to pop up 2 progress bars. When I tested it, popped them up right on top of each other, so I haven't moved the one to be able to see the other one. But basically, the outer one will increment, and then the inner one will increment all the way across, and then the outer one will increment again, and the inner one will do that. So I'm going to have one that's going to quickly be going back and forth, and the outer one's just going to go from 0 up to however many sample sizes I have it. But it's kind of nice to have the 2 progress bars, so I can see, okay, where am I in the replicate system, and where am I in this lapply? Okay, what steps are each place? So it's kind of nice with the object-oriented interface, is I can just have these 2 progress bar objects, and they both have their own variable I that's incrementing and keeping track of that. But since I belongs to the 2 different objects, they don't collide with each other, they don't have problems. They each know which progress bar to update, and it just keeps everything clean and separate. I just say when I want to increment the inner one, pd.I $, when I want to increment the outer one, it's pd.O. oh, and so it just keeps track of everything internally, and we don't have to worry too much about it. Okay? I can also add things after the fact. So here, if I do my prod bar and I call the set method on it, I can add to it. So here's another method. I don't have to redefine the whole thing. So you can do this in pieces as well. Here I've got my student sim function, and here I'm adding a new method that I just call stusim that does increment and then call stusim. And so now if I do the replicate, instead of actually having to call in and stusim separately, I can just call this stusim method of the progress bar, and it runs the stusim function and increments my progress bar inside of that. So this is even, tighter than playing golf, having as few strokes as possible. This looks a bit nicer there. But, so there's a few different options. And we get the active one. If you're just interested in progress bars, Progress package by Andrew actually runs, he did this to create wrappers around functions that keep track and do these progress bars as well. So, and it uses R6, I believe. So, okay. Another example, what's called memoizing, is saying, okay, when I calculate things, I might want to keep them instead of recalculating later on. So there's this class of functions called where a memoizing function remembers what is already calculated, and if you ask for something that's already calculated, it just gives that to you instead of recalculating it. So this is just a simple example with the Fibonacci sequence. And I don't know when I ever use the Fibonacci number, but it's great as an example. But there might be something else that works here. So here I'm just doing, so my first two Fibonacci values are going to be 1 and 1. And I currently have two values in my matrix here. And so now what I check is, so the fib function is actually going to say, so that's what I'm going to say is, give me the nth Fibonacci number. Okay? And so what it's going to do is it's going to test and see, okay, if n is less than self-cur max, so whatever the current maximum is, what I want to. If it's less than that, then that means that I've already calculated that value. So it's just going to return the nth element of my fib value vector. Okay? If it's not less than or equal to that value, then it knows that it needs to calculate some more. So here, I do the cat generating value so we can see the difference. If I was actually calculating these, I wouldn't do anything else. Then I just do a for loop where it says, okay, the current one is equal to, I minus 1 plus I minus 2. So the previous two values, add those together, runs through the loop, updates per max, and then gives that last value. So we can see when we run the code, so I do my fib here after the fifth Fibonacci number, and so that cat tells me, okay, it has 1 and 2, but it has to generate 3 to 5, and then it prints out and says, okay, the fifth Fibonacci number is 5. Then if I ask for the third one, it says it doesn't print out anything because it's already got that calculated. So it just prints out, oh, the third value is 2. If I ask for the 10th one, then it says, oh, now I have to generate 6 through 10. If you're ever doing something where you're going to call a function a lot of times and you want to save values so you don't have to redo it, this is one way to call memoizing it. I think it's a combination of memorandum and memorizing, and they call it memoizing. Right? I think somebody wanted to call it memorizing, and they just misspelled it, and they tried to justify it. This combination. Another quick example. If you look at the help page for the Optim function, it shows an example where it optimizes what's called I think it's the Rosenbach banana function, string function. And it shows that it can find the minimum, and that's this function right here. But Optim doesn't tell you anything about how it gets to that minimum. So I like to sometimes see this. So this is kind of self-education learning through here. So I create my own object here, RBF, or Rosenbach banana function. And I'm keeping x1 and x2 that start off as empty vectors. Basically getting my function here, and I probably should have told another name. So here I have x1 is the element, first element of this x, but then I have self x1 is going to be this x1 here. Should have renamed those. Should have been there. But basically, I say just keep it stored. So self x1, combining self x1 with the new x1 data. So this vector is going to be growing, and this is probably not the best way to do that, but it's only 50 or so, and it runs quickly, and doesn't mess up the memory too much. But so essentially, I'm going to have a vector of x1s that every time this function is called, and often calls this function with different values for x1 and x2. And so every time it's going to store those for me, and then it returns the result of the same function that you see in the Optim here. And so here I run Optim, and it finds, it says the minimum I found is essentially 1 and 1, which if you see here, that is 1 and 1 is the minimum, it's very close. But what I then like doing with this, hopefully this will stay here, so this is just plotting some results, but I get this plot out of it. Okay. So the color is the banana function, so it has this curved valley, and the minimum growth here, and it's really steep valley here, but it's really shallow going along the bottom, which is why this is a challenge for optimization. And so, but what I learned from this is just Optim, all it tells me is that this is where my final value was. But because I wrote my function to store in that, I can look at the resulting object that modified itself as this ran. And so this was my starting point, and I can see these are kind of the first 4 points where it's estimating the gradient by choosing 4 points. Then it says, okay, my best estimate of the gradient will come down here. I'll choose another point from these last few points, I'll estimate. And so you see it come down here, it bounces around a little bit, so it gets to the bottom of the value really quick. Have to bounce around a little bit to figure out, okay, what's my slope down here, and then it follows the bottom of this valley, occasionally backtracking, including doing different values, until it gets up here, and it actually overshoots and comes back. So it's kind of nice if you're saying, okay, well, what's going on internally? And, you know, the function that I pass to Optim, if I just pass a regular function to it, the only thing it can return is the result of the function. It can't return all this extra information because Optim will just get confused by that. So passing it a function that's part of this object is all Optim sees is the return value, but internally my object was growing, keeping track of all the x values that Optim passed it. Okay. Active bindings, I mentioned before, these are just the kind of the quick way to say a function that looks like a variable, and I used to do a lot more with Perl, and Perl has the syntax where you can say like x plus plus, and it says, give me the value of x, but also increment. And then also x plus y that says, so in R I can say x plus plus, I can say x becomes x plus 1, and instead of x plus equals y, I can say x becomes x plus y, but the shorter syntax is kind of nice and some ways to think about it. That's not available in R. So this was my way of saying, well, let's demonstrate this, because I like that functionality. There's also minus, but I want to keep this as short as possible. Okay. So I have a public value here, and it's just going to start at 0. Then active is my list of functions. Okay. And my active functions have to take exactly one argument. And when they're used, that argument might or might not be missing. It depends on if it's part of the assignment or not. So what I do here, so PP is for plus plus, and so it's a function value. And so I say if the value is missing, then that's similar to calling the x plus plus syntax. Okay? And so what I'm going to do is I'm just going to increment it by 1. So I'm going to say self value becomes self value plus 1, and then I return self value. Okay? Otherwise, if there is a value, then that's going to be the syntax more like x plus y, and so now I say self value becomes self value plus whatever value is passed over the function. Okay. So now I can use this here, so I can say my incrementer, x is an incrementer, I set my value to 5, then I have to say x $PP, so that's kind of my x plus plus syntax, and whatever returns is 6. And if I call this again, it would return 7, return 8. So forth. But here at 6, then if I assign 10 to it, so this looks like I'm assigning to a variable, and here it looks like I'm just accessing a variable, but internally it's really calling that function. Okay, so active functions, they're a little bit dangerous because they look like one thing and they're really something else, but they're really convenient when you want to use it here. So when I say assign 10 to it, it calls that function that actually adds 10 instead of replacing my value. So it's not going to replace the value of that 10. It's going to call that and add it, so the result here ends up being 16. So here's just a couple of examples of where I might use something like this in practice. So here I've got a while loop that I'm just running through. X starts with a big number. I keep replacing it with this square root to see how long it takes to convert to 1. But I'm testing if I plus plus is greater than 10. And if it is, I'm going to stop the loop and say I reach the maximum number of iterations. So a lot of times when we're looping and we don't know when to stop, we might put in something where it stops it. So I could have put in here some code that said, I becomes I plus 1, and then while I is greater than 10, do this. This makes a little nicer compact there. This is another way I could have done my progress bar is now just a value of I plus plus, and each time through this loop it's going to increment that by 1, and so that's something that's value there. So another compact way. And the rest of here, I think I lost it. What I want to do, so if you remember back to calculus class, before learning full integration, we learned the trapezoid rule, that you can estimate an integral by doing a bunch of trapezoids and adding up the area of those trapezoids, and that approximates the curve as you get the area of the curve. But in calculus, we just learned it where all these trapezoids are the same width, and where a curve is really curvy, it's better to have narrower trapezoids, but where it's not as curvy, you can have wider trapezoids. And so this is a kind of a recursive algorithm for studying trapezoids, but adapting based on what the curve looks like. So for that, I actually need 2 things here. So I actually have a little version of that. Okay. So here I'm setting up a trapezoid stack. I don't want to spend a lot of time here. I actually redid this with 2 different kinds of objects. I think I can find my other field. But here I'm setting up a stack where I'm just storing my left x and y coordinates and my right x and y coordinates. So each of these trapezoids, the bottom is going to be 0, the 2 sides are going to be vertical lines, and then the top will be slanted depending on my function. And so, and then I'm going to have a stack of trapezoids, and I have a bunch of these trapezoids. So the push function basically says add a new trapezoid to the stack. I'm not going to go into a lot of detail of those, but the top says remove the trapezoid. The trapezoid is on top of the stack, give it back to me, and you work with it. Push says put a trapezoid on that stack. So the code to actually run this with the adaptive integration here is I'm going to create 2 of these stacks. One is can for candidates. These are the candidates. These are the ones that I'm going to start with and say, can I get a better fit by splitting these in half? And then once they're small enough, I have a second one where as just a result. I like abbreviating things. So the results I'm going to put here. Okay. So here in my the function I'm going to be integrating for here, sine of x squared plus 1, just because it kind of looks cool. So I'm going to start off pushing on a trapezoid. It goes from 0 to 2.5, and the heights are my function at 0 and 2.5. My total area is 0, putting in a tolerance of 0.01 for decisions. We'll see down in the ladder where the tolerance is used. But I like to put those up at the top so that I can change those things. Okay. So my while loop is I'm going to look at the length of my candidate stack. So I started off by putting 1 trapezoid in the stack, So its current length is going to be 1. And if it ever gets to 0, that means I'm done. So that's why the while loop will end there. So my first step is I'm going to pop off the current one. So the first time through, I've only got 1. I'll be adding more later on. I'm going to pop that one off, and then I'm going to create 2 new trapezoids from that. So my new x value is going to be halfway between those x values, and then a new y one there. And I look at this, and then here I'm looking. This is everything. Basically, I say my estimated y from the trapezoid and my function value of y. If I look at how different those are. Okay. So when I split my, so I've got a trapezoid. If I look at halfway through and I look at the height of the trapezoid and I look at the height of the function, if they're pretty close to each other, then I'm going to say the trapezoid's already a pretty good estimate. But if they're far away, I'm going to replace it with 2 new trapezoids, splitting it in half. So that's what my if here is. So if this distance, so that's the value of the difference, is less than that tolerance, then that means I'm done. So I'm going to push the results onto the results. So this is the left trapezoid and this is the right trapezoid. And I'm going to add my area. Otherwise, I'm going to push both of those trapezoids back into my candidate. So my first time through, I'm going to have a really lousy fitting trapezoid. So I'm going to split it in half, put both of those back on, and then the next time through the loop, it's going to pull one of those out, and which I split this. I probably will, and put both of those back on, and do that. It's going to keep taking whatever one I pushed on last, pop it out, split it in half, until it decides that it's close enough, and then it's going to say, okay, these are close enough, so I'm going to put it in the result set, and go and take the next one from the candidate. Again, all of this really is a fun. So I can run this through, so that's just here. So here is my, so the green line is the function, and the blue lines represent the trapezoids that got out of here. I had an animation which you can actually see the trapezoids growing and shrinking there. It's kind of interesting. So through this section here, you can see the line is pretty straight. And so these 2 wider trapezoids do a pretty good job of estimating what's going on. But over here, we have a lot, it's a lot of curvature, so we need a lot of really big trapezoids. And here, we need a little bit thicker than those ones. These ones are a little bit thicker, these are the thickest ones. So you get this adaptive thing where, I started off with one trapezoid that basically looked like this, with a lousy bit, and then I said, okay, halfway through, and so it splits the trapezoid like this, and then another one like this, and then it takes this one, splits it in half, and keeps going down. But it gets here to say, oh, hey, these 2 pretty close. I don't need to shrink those anymore. Work with these. So you get kind of interesting ideas with these widgets. If you're interested in things like stacks, the R6VS package implements stacks, queues, W-linked lists, DQs. There are a couple other things. It uses R6 to create these things rather than creating a stack like I did. You use it built-in ones that are a little bit different. So some of the things I didn't cover here, inheritance is where I created a trapezoid stack and they want to do something with rectangles instead. And I say, well, my rectangles are well like trapezoids, so rather than rewriting the code, I could say, well, I'll create a rectangle stack that inherits from the trapezoid stack. And so everything that's the same, it just gets there, and then I can write new methods specific to work on my rectangle. Debugging is a little bit tricky, but a lot of the same tools work. You can add in, cat and print statements. There is a debug method that you can set things to debug. So if you're doing this like in RStudio, we'll bring up the debugger and trace through your code. So we'll spend a lot of time there. You can do what are called non-portable R6 objects. I try to make everything portable. That's where I specified everything as self-$on or private $on. It just makes everything cleaner. And if you're going to inherit or work with other packages, you need to do that. You can make things sometimes a little bit easier by making them non-portable. There's lots of theory and there's a whole computer science course on object-oriented programming. everything, but hopefully this shows kind of some of the fun parts of doing it that give you some ideas and some things to play with. Again, I don't think I have direct access to GitHubs, or so I'll send those tomorrow. So, any questions?
Great, thank you so much. Does anybody have a question to get us started? I'll start off questions. Can you give me, like in your, so I work mostly in with real life messy data, analyzing it, making graphs, training models. What are some examples where you use, you create like methods or like object methods in that kind of like workflow in real life?
For actually like statistical analysis,
Yeah.
what exists is already pretty good, and I don't know that we need much there. So this is much more for when you're doing the programming and you've got an unusual type of data that you need to convert into some other way, and you want to keep something along the way. And again, part of the reason I wanted to present on this was to learn that I've seen it, and I've played with it a little bit, I want to learn more. I haven't used it a whole lot. So after putting this presentation together, I actually had an idea that I've been thinking about for a long time. And said, hey, this R6DS package is great. It helps with things. So I actually wrote this little program where I started off with a square with 4 triangles in it, and then I compared a picture. I had a photograph that I'd taken, and it basically would take a triangle and it would split it in half, make 2 new triangles, and it would give me the color of the triangles based on the average color in the picture for that same area. And then if the variance within the triangle was small enough, which I'm done, otherwise it would put it back on the stack. I used to keep this in the stack to look at future split. So I start off with 4 big triangles and it keeps cutting into smaller and smaller triangles. It would look cool to watch. So I started with this photograph of some flowers. So this part was green and this part was purple, and there's a little yellow one here and there. And it gets down to all these triangles that each triangle is just one color, but then it kind of captures the picture in kind of an abstract way. And then I showed it to my wife, who's a quilter, and the first one I showed her, she was like, yeah, not so much. I've done a little bit nicer picture and did it. So, okay, that one I'm going to turn into a quilt. So I used art to design quilts for my wife. I like to send pictures out of it. A lot of this is, it's more when you're getting into some of the programming things and you've got a longer thing. I like it for sometimes just the learning things where I say, okay, this function is a black box to me, and I know I'm passing this in, and I want to know what's going on inside. So creating the object, like I did with Optim, is that's a way to peer into the black box. It's kind of like setting a camera into the black box to take pictures of what's going on. So we can see that the path there. The memo, if you want to memorize, keep track. Sometimes it's just a nice wrapper. I've done some other projects since putting this together, where now I'm using the code I put together for, the progress bar. I'm having it do that. I like progress bars, but I like the syntax better than the original. For doing the regression, scatter plots and that, I don't see much use for using it there. So I thought it would be kind of cool to do a regression object where, right now you do regression and you do summary and then you do plot. We could have an R6 type object where instead of calling plot on my regular LM object, now I would say object $plot. And it would essentially do the same plot, it would just be a little different syntax. Not only doing that.
No, those are great examples. Any other questions?
Yes, we're going to put it on a GitHub page that's associated. So if you don't really know where it is, if you just Google for City or SLC GitHub, it takes you right there. So Mark's going to put it up. Yeah. Yeah, so you can overwrite something. You want to be a little bit careful doing that because, you've already got some objects there. They can mess things up there, but just as you're creating it. So most of my examples, I just created it all in one thing because I did a script file. Most people are small, but you can after the fact, instead of doing it in one big step, you can create the basic and then call the other functions to,
All right, that's good. And I got you one more opinion question. So in the package that I developed, I've had people say like, oh yeah, S3 is fine to me, something simple. R6 is good. And I've had, everyone I've ever talked to has been like, stay away from S4, like don't go there. What was your experience with it? Do you agree?
I agree, but I recognize people who really like S4 that come from that side.
Yeah.
I can see why they like S4 and but you know, inertia, I like S3 so much.
Yeah.
If I'm going to move beyond S3, I like jumping all the way to R6.
Yeah.
I think R6 is cleaner
Yeah.
now and easier and simpler than S4 was just having to go in and you know, you had to set a class and then you had to create the class and you had to set methods, you know, you had to register all these things. It just seemed cumbersome to me.
Yeah.
All of a sudden, R6 is doing kind of the same thing, pulling, you know, registering it in that, but I think it's simpler.
Yeah. All right, well, let's thank Craig.